Our final section in this chapter is to introduce the idea of what we call redox, or more formally, oxidation reduction reactions. Oxidation reduction reactions are a specific group of reactions that involve a transfer of electrons. And in some redox reactions, it's very obvious where the transfer takes place, and sometimes it's much more hidden. So we'll start with one of these examples where it's relatively obvious. So zinc metal plus copper 2 plus reacts to form zinc 2 plus copper. So what we can see is that the zinc was neutral and then became +2. And so in other words, the zinc lost 2 electrons. We can contrast that with the copper, which started at +2 and became neutral, and it gained 2 electrons. So when a species gains electrons, like the copper did, we call that a reduction. And when it loses electrons, that's known as an oxidation. In addition to that, let's put the reaction back up here. The zinc, we said zinc is losing electrons, so it's being oxidized. The zinc is also here known as our reducing agent. It's our reducing agent because it's the substance that causes a reduction to occur by donating its electrons. The copper, on the other hand, is known by the term oxidizing agent. It's referred to as the oxidizing agent because it's causing something else to be oxidized by gaining electrons. So as I said, sometimes it's very straightforward to figure out which one's being oxidized, which one's being reduced, because the charges are right there in our ionic equation. On the other hand, a reaction like the following, magnesium plus O2 forms magnesium oxide. This is also an oxidation reduction reaction. It's not as obvious because we don't see any charges present. So how do we know that there's a transfer of electrons? Well, the first thing Metals are very, very commonly reducing agents. They like to give up electrons. And it turns out you can split up any redox reaction into two half reactions, and that means we show the oxidation in one reaction, the reduction in the other half reaction. And what we find here is that the magnesium is being converted to magnesium 2 plus 2 electrons. On the other hand, nonmetals, which of course oxygen is one, generally like to gain electrons. They often serve as oxidizing agents. And here we find that O2 plus 4 electrons forms 2 oxygen 2 minus. Now in this case we can fairly easily balance this equation. Turns out balancing more complicated redox reactions is actually fairly complicated, and that's something that you'll see in the end of general chemistry too. Now, I was able to show you these two half reactions because I know that that's what happens. But if you didn't know that, how would you determine what was being oxidized, what was being reduced? So we would need to know the following rules. And these go under the heading of what we call an oxidation number. An oxidation number is the charge an atom would have if it was an ion. So, number one, an atom in its elemental state has an oxidation number of 0. Now, what is its elemental state? Depends on what the element is. That could be something like hydrogen or oxygen. Those would be H2 or O2. For a noble gas like argon, it would just be a single atom of argon, and various other things for different elements. But if the element is in its elemental state, it has an oxidation number of 0. So if you think back to our previous reaction, one with magnesium and oxygen, both magnesium and oxygen are in their elemental states, and so they both have oxidation numbers of 0. All right, number 2. In a monoatomic ion, charge equals oxidation number. So sodium plus would have an oxidation number of 1. Calcium 2 plus, an oxidation number of plus 2. N3 minus would have an oxidation number of minus 3, and so on. Now, the following are a number of general rules that we'll follow most of the time. Halogens are usually -1. Group 1, usually +1. Our group 2 elements, generally +2. Hydrogen is usually +1, but if it's with a group 1 or 2 metal, then it's -1. Oxygen is usually -2, although there can be some exceptions. So again, we're going to go back to our example now. On the right side of our equation, we had magnesium oxide. So if we now know that oxygen is normally -2, then what does magnesium have to be? Well, if the compound magnesium oxide is neutral, then all of those oxidation numbers within the compound need to add to 0. So if oxygen is -2, magnesium +2. And so now by looking at the oxidation numbers, we can see that magnesium started at 0, ended at +2. So magnesium lost electrons, or magnesium was oxidized. Oxygen started at 0, ended at -2. So we can see that oxygen was reduced by 2 electrons. And so we can do a couple more examples as practice. So PCl3. What we're going to do is calculate the oxidation numbers of each element here. So halogens were one of the things that we identified on the previous page. Halogens are generally -1. So since there's 3 of them, that's -3 total. The overall compound is neutral. So to balance that out, phosphorus would have an oxidation number of +3. How about KMnO4? So potassium is one of our group 1 metals, oxidation number +1. Oxygen, we've already said in most cases, is -2. So in total here, we have 4 oxygens at -2 each, and 1 potassium at +1. So the atoms we know give us a total of -7. That means the remaining element, the manganese, because the potassium permanganate is overall neutral, needs to equal out to whatever value it needs to be to make it neutral. And the only way that it becomes neutral is if manganese here has an oxidation number of +7. We'll do one more example. How about sulfuric acid? So hydrogen, recall, is +1 unless it's unless it's with a group 1 or 2 metal. We don't have any metals here, so each of these hydrogens +1. Oxygen, we've said, is generally -2. So we have 2 times +1 from the hydrogen, 4 times -2 from the oxygen, means we have -6. So the sulfur needs to be whatever value to get back to 0 because the overall compound is neutral. So sulfur here has an oxidation number of +6. So the final thing I want to show you in relation to oxidation reactions is what's known as the activity series. And you can see that here. And the activity series is basically just a list of metals and their ability to be oxidized. And the way that we look at this table is the higher the element is on this table, the more reactive it is, the more it wants to give up electrons. As you get down to the bottom of the table, those elements, copper, silver, gold, they're the least reactive. They're the most difficult to oxidize and the least likely to lose electrons. And so you can use this table to determine in some cases whether a reaction will be able to take place or not, depending on where the element is in the activity series. So what do I mean by that? So let's say we wanted to know, will aluminum react with KCl? So the aluminum right now is in an oxidation state of 0, whereas potassium is +1 and the chlorine is -1. So for this to react, the aluminum would need to give up electrons to potassium. In other words, for this to react, aluminum would need to be oxidized. But if we go back to our activity series, we can see that aluminum is not as reactive as potassium. In other words, potassium is more willing to give up its electrons. So will the aluminum react here? The answer is no. Would it go the other way? So what if we had aluminum chloride plus potassium? Well, in order for this to react, the potassium would need to give up electrons to the aluminum. Going back to our activity series, we can see that potassium is more easily oxidized than aluminum. So yes, potassium will react. So another way to think of this is that any metal will react with an ion that is below it in the activity series, but not one that's above it.